Now, these two things I've written on the board really seem like the same thing. I've just drawn two different versions of this molecule. The only difference is that in one case I've got the substituents pointing to the left, and in one case I have the substituents pointing to the right. But this is the same molecule in both cases, so why should I draw it in two different ways? Well, this is just to show there's two different ways that the dienophile could approach the diene. There's two different approaches that the dienophile could have to the diene. There's one approach where these substituents are pointing into the diene. And then there's another approach where the substituents on the dienophile are pointing out of or away from the diene. So even though these are the same molecule, if we do this approach, we're going to get a different type of product than if we do this approach down here. Now, let's see. So would we call this one the endo approach or the exo approach?
Exo. Oh.
Now, are these substituents, do they look like they're pointing into the diene or out of the diene?
Into.
Into. Here's the back of the diene over here. So pointing into the diene is pointing in this direction, towards the back of the diene. So this picture would be the endo approach because these substituents are pointing into, endo stands for into the diene. Endo is when the dienophile substituents are pointing into the diene. And the exo approach is when the dienophile substituents are pointing away from or out of the diene. So does it make sense that these are pointing away from the diene? Now you know that exo means like exit. An exit is how you get away from something. So these are pointing away, trying to get away from the diene. So we can draw our mechanisms here. I also put in a bunch of inside substituents here just so we can get some extra practice with that. Remember that the inside substituents, these are not participating in the Diels-Alder reaction. They're just substituents. It's these asterisk carbons that are actually participating in the reaction. Now, in this picture, I chose to put this inside substituent on a wedge. So does the other substituent have to be on a wedge too? Yes, because they were both inside. Retention of configuration. Since they started in similar positions, they should end up in similar positions. So if I choose to put these on wedges, they should both be on wedges because they both started on the inside. Now,
wait, aren't they on the wrong carbon?
These? Yeah. Here, the asterisks help me to see that they're on the right carbon. Maybe I should have mentioned something a little bit more here. Let's go back here. I guess I wasn't quite ready for this. Let's back up for a second. So if this is our general picture of a diene, this of the substituents on a diene, this could be our picture of the substituents on a dienophile. Does it make sense that I would call these two substituents the endo substituents? Because they're both pointing into the back of the diene over here. And I would call these two substituents the exo substituents because they're pointing away from. So these terms here are in relation to this diene that we've written over here. So you can see now we have names for the substituents on both the diene and the dienophile. On the diene, we use the terms outside and inside. And on the dienophile, we can use the terms endo and exo. So these two pictures go together. Now, we need to have retention of configuration. What have we talked about before? Well, we've talked about what happens if we've talked about the relationship between two substituents on the dienophile. If they both are start cis, they end cis, for example. And then after that, we talked about the relationship between two substituents on the diene. If they both start on the outside, then they both end up cis to each other. But now we have to talk about the relationship between one substituent on the dienophile and one substituent on the diene. That's the last relationship that we haven't talked about yet. What's the relationship between a substituent from here and a substituent from here? Well, we still have retention of configuration. So the substituents that started similar to each other will end similar. And the substituents that started different will end different. The only thing we have to do is we have to articulate what does similar mean in this context. Well, which of these two substituents is more like it's pointing, is closer to the back, basically, of the dienophile? Which of these two substituents is?
Outside.
Yeah, it's not really pointing to the back, but at least it's not pointing away from the back. Maybe a better way to put it is, these inside substituents are definitely kind of pointing exo. These inside substituents are definitely pointing away from the diene. So these kind of correspond to the exos over here. We don't call them exo, but they correspond to the exos over here. So our rules are the inside position on the diene is similar to the exo position on the dienophile. And the outside position on the diene is similar to the endo position on the dienophile. And that kind of makes sense. It certainly kind of makes sense that the inside is kind of pointing away from the back portion of the dienophile here. So the outside is all that's left to be closer to the inside. It's not literally pointing towards the back, but at least it's not pointing away from the back. Or we could just memorize inside is similar to exo and outside is similar to endo.
Like the opposites.
All right, so if I choose to put this substituent on a wedge, where should I put the substituent on the dotted at? Dashed, because this was pointing into and this was pointing away from the back of the diene. Inside and endo are kind of opposite to each other over here. So all that work that we just did was to figure out the relationship between the substituent on the asterisk carbon and on this dotted carbon over here. If we choose to put this on a wedge, this should be in the different position, because they kind of started in different positions here. This kind of was pointing away from the back of the diene, and this was kind of pointing towards the back. So you can see how we can keep using this idea of retention of configuration for all the different types of stereochemistry. Now how about the other CF3 down here?
Dashed as well.
Because it was, again, pointing towards the back, whereas this was pointing away.
So it's meso.
Ah, and this is meso, so is there another product?
Nope.
No, since it's meso, there is no other product. Okay, so that was our, that's the last piece of stereochemistry we have to work with. What's the relationship between substituents from one molecule and the other one? And that's where that endo and exo idea comes in. So, okay, so this is the only product. Good. Now we have to draw the exo product or products. So let's draw what our exo product or products would be down here. Because in this case, I oriented the substituents pointing away. So here we should get the exo products. Looks like you already did that. Now you can put this on either a wedge or a dash. I'll choose to put it on a wedge. But if I put this on a wedge, this has to also be on a wedge because they both started similar to each other on the inside. And now these substituents are similar to these substituents over here. These are pointing away from the back of the diene, and these are pointing away from the back. So if I choose to put these on wedges, these should also be wedges. And is this meso?
Yes.
So there are no other products. So this is the only, in this particular case, there's one endo product and one exo product, and that's it. If I wanted to, I could have drawn these all on dashes. It doesn't matter. The key thing is they should all be in the same place. So how could this be tested? Well, now, I don't want to give you the idea that there's usually a lot of information about which way this is drawn. I just happened here to say that this is how it would look endo and exo, but you're not usually supposed to say, oh, this is the endo just because these substituents are pointing this way. Here's how it's really tested. The problem might say, draw the endo product. Or the problem might say, draw the exo product. Or the problem might say, draw all possible products. Those are the three variations. So if they say, draw the endo product, you would draw this. And if they had said here, draw the exo product, you would draw this. And if they had said, draw all possible products, you would draw both of them. They don't usually signal whether something is endo or exo just by the way the dienophile is oriented. That's usually arbitrary. I just happen to orient them this way because that's consistent with these ideas of endo and exo. But they'll usually use words to tell you which approach that they want. Because after all, even if they happen to draw the molecule like this, it could easily rotate in solution to approach from the other direction.
So if the molecule was not meso, then we might have 4 products?
Absolutely. In fact, the maximum number of products you could ever get from a Diels-Alder is 8. We haven't done anything that complicated yet, and I'm not sure whether that would actually come up in your course. But there's possibilities for lots of products, never more than 8. But yeah, if these hadn't been meso, we could have gotten 4 products.